Okay, here we go. This is a video about a pump for a well, like an open top dug well in your backyard. Very popular in the Philippines. We have a lot of dug wells, not too many drilled wells. Thing with a manual pump is it only brings water up 27 feet. It's got to do with the way a pump works. You basically have the atmosphere pushing down on the surface of the water, and you reduce the pressure on the side you want the water to come out by drawing a piston cup up. It sort of makes a vacuum, and so that's the maximum that you can pull up is what the difference between atmospheric pressure and the pressure that you can reduce it to. If you want to go deeper, say you had a 30-foot deep well, and you got a pipe going down in there near the bottom. When the water level in the well falls to around 27 feet from the base of the pump, it'll quit pumping. It pumps slower and slower as it gets to that point. Obviously, it pumps the full volume of the pump if it was only the water was only down 2 or 3 feet from the bottom of the base of the pump. So what we're going to do is we're going to put the pumping part down in the well, and at the bottom of the well, you can use like a 6-inch core auger or something like that, and you can drill down in the bottom of your dug well another 10, 15, 20, up to 40 feet. You just keep on drilling and put a piece of that black PVC pipe in there with some holes drilled in the side. And so your pumping parts will be at the bottom of what the original well was, or if the well was at 40 feet, it's still at the bottom of the well. And you can extend the pipe down deeper from that, rather than keeping on digging that big hole. But you need some storage volume is why that works. So let's look here at the pumping part of it. And what's on my screen and what's on your screen is different. Well, let's just go into the parts. We have a pipe union, and the bottom of that would be the pipe going down that the water's being drawn out of the well from. And you have a piece of pipe that connects it, and you have a swing check. This is a combination horizontal, vertical. I don't think they really make a vertical swing check or check valve, but this works only by gravity. There's no springs or anything to overcome, so they won't cut the efficiency on what's going on. So we're going to use swing checks. There's the first one. So when the water gets, what's it doing? When the water gets drawn up the pipe past this check, normally this thing would be held down by gravity. It would have fell over the hole here. Anyway, the water goes up through here, and when the water stops moving, then this little door falls closed, keeps the water from getting back out. And then we're going to come up, piece of pipe to connect things together, and this is the pipe tee. I drew these as hydraulic tees because they have real thick walls, and they're also available in stainless. And either you need a lot of metal and stuff that you're not going to want to do maintenance on, or it needs to be out of something that the environment won't damage. You can use stainless, and they tend to be fairly thin. Probably not much thicker than a regular elbow. Anyway, from the T, we go to the left, and elbow up into a cap. This everything so far was just right off the shelf plumbing. These couple 3 pieces here you have to make. You can buy a used hydraulic cylinder or air cylinder to use for this part. But I just chose to draw one up because I got a machine shop here, and I got one at home too. And we would just make them. This is a solid block, probably 3/16 stainless. It's got 3 O-rings, a 187 cross section. They're 4-inch on the outside because this piece of tubing here comes in 4-inch. Okay. In the tube, the pumping part, we have 2 pistons. I should have made these different colors so the parts show up. That was just an error. If my videos didn't run so long, I would stop and do it right now. How much time we got? I don't want to get into that because it's going to make the video run long, and if I pause it, I have to figure out how to put it back together. I can make them, I just can't edit them. Okay, so we got one piece up here, goes down to fit the cup seal, and then you have a washer on the bottom that comes up against the cup seal, and this is piloted. Doesn't show here because everything is assembled. If it was a cross section, you could see it really plainly, but this bottom piece goes into the top piece, like it telescopes in and out, and the hole in the side of this cup seal, which you can buy at Nazareno's Hardware or place like that, that would be the diameter that you make that. The 4-inch on the outside is fixed. There's about 90 thousandths of an inch, 2 millimeters or so clearance on the piston. This here is the cup seal. It's got a sharp edge on it. It's sort of U-shaped, dish-shaped. And then there's a 3/4 fine thread nut on either side. And when you tighten those nuts, it crushes all that together. To avoid having to have a packing gland and a runner bushing and all that stuff on the other end of the cylinder, to simplify it, and also do away with maintenance, because that's where your maintenance comes, is on that piece there. The cup seals, they tend to wear after a while, and eventually they start drawing air. But we've cured the drawing air part. This thing won't draw air. Let's see here. It's going to make sense in a minute. Okay. Okay, this is the part that does the actual pumping. And it goes down, and when you pull it up, it sucks water underneath. And then the check valve closes. The lower one we looked at closes. Then you push it down again. And it pushes the water back towards the T, but it can't go down. So there's another check valve right above the T, and it goes, the only place it's got an outlet is through that check valve. And then it goes up to the top of the thing to wherever you're collecting your water. But the trick to it is running this thing up and down. Okay? I'll just leave it where it's parked. Now, there's going to be a fair amount of water weight on the water going up, because you got water going up 30 or 40 feet from this pump to the top of the well, and all that water in that pipe, you have to compensate for the weight of that hydrostatic pressure, because the handle will work really easy one way and really hard the other way. Where's the? Yeah, when it comes out this other check valve, there's your second check valve. It's above the T. Now the water's in this pipe, and that's just a union to connect the other pipe going up. The weight of the water from there to the top is pushing on your works down here. Now to counterbalance that, here's the first trick. Where the rod runs up and down, we don't have to seal the rod. It's not sealed at all. It's got an 1.5 inch hole with a 3/4 inch rod, completely open. You got a pipe just like you had on the suction end, a union so that you can attach a pipe, and then a pipe screws into this union. It goes clear to the top of the well, and that stays full of water. So the height of the water on the pumping side and the height of the water on the discharge side is the same. So there's no weight difference, no pressure difference against the piston in here. So your handle will stay pretty much any place you stop pushing it. It'll be just free in there. And this rod here, the purple rod, is the one that connects to the 2 pistons in the pump. This is a what's called a tall nut over here. And this is another piece of threaded rod. That's so you can take it apart. Like if you had to take this thing out for service, or somebody 2 generations from now finally has to work on the thing, you have 3 pipe unions to take apart, and they'll take it out of the well. This pipe here, you slide it up, because this thing has to be able to come down enough to push the pistons into the bottom. I keep looking at my screen, but I got to realize that there's another screen here. So we're not even looking at the thing I'm talking about. It'd be easier if I made this thing up and just had it on the table and made it out of metal. I'm going to do that shortly too. Anyway, this piece of pipe at the top with a union, and that's just for a pipe running up to the top so you can have the hydrostatic head of water, counterbalancing the water that you're pumping. So it makes it fairly easy to pump. Water goes up and down this pipe, but it doesn't get out of there because of this the piston blocking the bore. And the water from here can't go down below this check valve because it's a swing check. But it can come up in there and be above that. When this purple piston comes down, it pushes the water around that and back up here and out of the well. And I know somebody's going to tell me that I could have made this a lot more efficient. And you're right. So let's do that. Suppose we take another check valve set. This is the same vertical piece here with the 2 check valves and the unions, the same piece of pipe going across, but this time we got a T here. Where we had an elbow going up into the bottom of the pump, we've got a T. And the purpose of that we take this contraption over here, this whole thing, and stick it in here. Where that union is, it would go, the T would go there, and at the top of that you'd have a little piece of pipe, and then the union for maintenance. Now the difference between this and the other set is we have to stop water from going up and down the drive rod. Otherwise it won't pump. So let's go over here and take a look. And I've got a written note here. There's all kinds of notes on this part because this is for the machine shop and other people. Okay, this piece here that was a pipe, it looks like a pipe, is not a pipe. This piece of aluminum bronze. aluminum bronze is a bearing material. This is cheaper than regular bronze and a lot harder than brass. Brass has tin in it. Tin's very expensive. It's a precious metal. It's not up to the price of gold, but you recover tin when you're doing recycling of metal. They electroplate remove it, and because it's a really expensive thing per ounce. It's right under silver as a precious metal, so you don't want to put a lot of tin in your bearing. And so they replace some of it with aluminum. So aluminum bronze has got aluminum, and the tin that would be in brass, and just a few things. Anyway, this is a solid piece of shaft. The outsides are threaded to 1.5-inch pipe. All these pipe fittings are 1.5 inch because you got a 4-inch bore down here, and if you necked it down to 3/4 inch or 1/2 inch pipe, it would really be hard to push, and you'd be raising so much pressure in the cylinder. Some of it would go past the cup seals, you'd be pumping for nothing. So we use 1.5-inch pipe in this. It's also, 1.5-inch pipe is fairly stiff, and you don't have a lot of supports on it going up the well. Anyway, this piece is aluminum bronze. It's drilled and then reamed to about 2 thousandths bigger than this 3/4 inch stainless rod here. So this is the bearing. It's the guide for the rod, and it blocks the water from going up and down this pipe here. Now, I could put a seal on it, or a wiper seal, or an oil seal. A lot of things you could put on it, but they all take maintenance. And it would work without it, and it would work better with it, but it's going to work without it. It's just like 90% efficiency rather than 100. Well, it's on my screen, but not yours. Yeah. So here's a little fella installed in the pipe. This is exactly the same pipes, check valve, T, unions on the ends, same piece copied. Now, just to make it look like they're not connected, I drew this pipe up as being longer. Actually, these pipes would probably be the same length, and you would clock it. You would turn this T around so that this thing and that thing are sort of beside each other. This check valve set and that would have you two pipes running up to the top of the well. Or you could try to put it together with pipe fittings and have a single pipe going up. I choose the two pipes because you have two independent pumps. You have the top section pump and the bottom section pump. If you damage the cup seals or they wear on one side, the other side still works. If this check valve here gets a bunch of gravel and stuff in it, and it's not sealing off, and the water tends to run, well, some of it would run back because the other, if either one of those check valves is working, the water can't get back to the bottom of the well to stay in the pipe. But once both of them are leaking, then you'd have to prime it to get it going again. And being that it's down there right at water level, priming is not really a problem. But having the second piece of pipe makes two independent pumps down in the bottom of the thing with one push rod to drive it up and down. And this is the same deal with the push rod. If I've drawn it connected, goes up and down. Okay, we got some notes here. What do we got in notes? This is the size of the O-rings and the working parts. Well, it's just 4-inch O-ring, 4-inch cup seals, 4-inch ODO rings. Takes 6. I drew it up as 3 on each block because the piece of material I selected out of the scrap pile allowed me to do that. Oh, there's another thing here. when this piston comes down, I don't know if you can see the lines in that part, but this can fit down in here, and you notice how that. Let me leave it down there. Okay. This shoulder sticking up here off the this bottom cylinder gland or whatever, it comes up against the washer. This is old hydraulics trick. It's and still works good today. As this washer right here comes down to that, it starts closing off. The place for the water to escape gets less and less and less. And just before they touch, you really have to force that water to go out that crack. It can't go anyplace out here because of the cup seal's got, the cup seal fits over this edge. That's why this has got relief on it. It's for the cup seal to go to. So the water can't get out of this place. It's trapped between these two plates. And that gives it a cushion so that it doesn't slam. And in hydraulics, you let it close off. You'd actually have this this nut would be a round thing that feed into a hole. It'd be beveled a little bit, but it went in the whole way to block the hole. And then all the oil in the hydraulic cylinder come down here to a little bitty hole drilled here that goes down past that. And every bit of that oil has to go out through that little hole. And that keeps the parts from ever really getting to each other. I don't know if I have parts in this drawing. May have. Okay, let me get rid of some stuff here. Nope, it's all joined together. Group. Okay, we got a nut on one side, got a nut on the other side. Got some lines here was used just to draw it. They got brought over with the part. They're not any concern to us. This is the line it took to draw that. A lot of times I'll leave those in the thing so that I can make changes so I don't have to redraw the whole blasted thing. lines we drew it with. Don't need those anymore. Okay. So this red thing is the top half of the piston. There's a hole in the cup seal that fits over that. And this is countersunk here to let the red thing fit in it. And the difference in height here is less than the thickness of the cup seal. So that's how that works. Yeah, and of course I didn't have it on the screen where anybody could see it. Okay. The red thing is the top of the piston. It's a solid chunk of metal machined to that shape. The purple thing is the cup seal. It's got a knife edge on one end. And then the blue thing is the washer. This counter bore here fits over top of this red thing. And this purple thing is the cup seal sandwiched between them. And jamming the nuts down locks it all together. And these would be steel lock nuts. So that's what they're drawn up as. No plastic in the threads or in the top of the nut. It's just an interference fit on the threads. Probably take 25 foot-pounds down to the last couple threads just to turn them to get them off. I don't know what we're looking at, but it's not this. This is a 3D view of the same thing, the same part we're looking at. Got a pipe unit at the bottom, piece of pipe to connect it, check valve, piece of pipe to connect it to the T, piece of pipe connects to another check valve, piece of pipe, and a union. All hardware store stuff off the shelf. This can be black iron pipe, it can be anything with 1.5" threads on it. I chose stainless because it lasts nearly forever on this application. Got a piece of pipe coming over. This is showed as a 4-inch long piece of pipe, but 3 would work. 2 inches on 1.5 inches would be close nipple. So I don't know if I would go that far. That's showing you that the pipe's got an elbow going into the this bottom plate. It's 1.5" threads. I just drew it like I had a 1.5" pipe die, but I don't own one. So what that's actually going to be is we're going to counterbore this blue plate for a hydraulic coupling, and then press it in there and weld it or braze it into the bottom, either one, and that'll give us the threads. And we're not worried about this height here. It doesn't make any difference. It's not a critical thing. And this top gland is a mirror image of the bottom gland. There's a bunch of stray lines in this. I was more interested in keeping my train of thought and getting it down to where I could when I get a cup seal after lockdown, I can put the dimensions on those 2 interlocking telescopic flanges. This is drawn up with tie bolts. 1, 2, 3, 4, 5, 6. I don't know why I do it as 1/2" threads or 1/2" tie rods, which are way too big for this job. Oh, you can't see it. I'm good at that, aren't I? I ought to get some kind of credits for being unclear on that. And we'll back the narration up. Okay, here we go, forward again. 1, 2, 3, 4, 5, 6 holes. That's for tie rods. They could be 4 instead of 6. I just like 6. but it could be 4, no problem. The thing is, we can only get a couple of sizes of threaded rod here. 1/2 inch and 5/8 are easy. Almost any hardware store has them. When you get to 3/4, about half the hardware stores have them. You can get 3/8, and if they haven't got it, they can get it in a couple days. I could use 3/8 on this. It's plenty strong, but it's just a matter of longevity, how long it would last on underwater. Most of the threaded rod, you order threaded rod, but it comes stainless. It's not mild steel threaded rod. If I was to make this a shaded view, then the parts would look more like parts. I don't know how long it's going to take to shade. I click shade, but we can talk about our crap here while it's going on. O-rings are probably Buna N or neoprene. They don't have to be Teflon encapsulated fancy stuff, just regular rubber O-rings. They're for water service, not high temperature. Anything that doesn't dry rot will work. It's going to take forever to render that. Let's cancel that. It may not even let me. If it's close to done, it won't let me cancel it. And I guess it thinks it's close to being done. No, it let me cancel it. How about we're going to cancel this too. It's at 20%. This is rendered. This makes a 3D picture out of your drawing. 40%. 50%. Well, let's let it go. I guess they had to have that same mesh on the drawing. 60, 70. He's working on it. Thing is, I won't be able to move my view. It's a snapshot. You would save it as a JPEG. Always throw a bunch of them into the pile of paperwork for the machine shop so they can see what something looks like put together. Picture worth 1,000 words. If nothing else, we'll see how long it takes to render a... The reason this is taking so long is there's